Okay, so let's do this problem now. So we want to find the Green's function for this problem. Okay, so I want to just talk generically. I'm probably not going to have this written up in the solutions. Maybe I'll keep it, I don't know. But here's the idea of a Green's function. So the Green's function for the problem, L phi equals f, with boundary conditions, with homogeneous boundary conditions, is the solution to the following. So it's going to say Lg of xy is equal to the delta function of x minus y, and plus g satisfies the same homogeneous boundary conditions. Now, in addition to this, if G satisfies these things, then we can conclude other things about it. For example, we can conclude that it is continuous, and if we integrate it, we get 1 on the right hand. If we integrate over y with respect to x, we get 1 on the right hand side, and we get whatever we get on the left hand side, and so we can use that to help us to compute what G is. But this is the problem that G satisfies. Okay, so why do we care about that? So if, what are my letters I'm using here? If phi of x is equal to the integral from 0 to 1 of f of y, f of y, g of x comma y, then what do we get? Okay, then what do we get when we do L phi of x? Well, L is an operator in the x variable, so if you just do L times the integral here, there should be a dy there, right? No, sorry, yeah, dy. So if we do L to this, and we move L to the inside, so L is an operator in the x variables. It's like differentiating in the x variables, so we can move it to the inside of the integral, at least formally. So we get an L here, because as far as L is concerned, f of y is a constant. And then what is this? This is the integral from 0 to 1 f of y delta of x minus y. Okay, why is it delta of x minus y? Well, that's what Lg is defined as. That's one of the things that it defines. It satisfies those properties. Okay, well, what's that equal to? Well, f of y times this integral here, f of y times delta of x minus y, this just says, this is the delta distribution centered at x now. Okay, it's either, if x is the variable, it's the delta distribution centered at y. If y is the variable, it's the delta distribution centered at x. Y is the variable, since that's the variable of integration. So what this says is wherever you see a y on the other part of the integral, just plug in x. So this is equal to f of x. Okay, sorry about that. I don't know, I forget exactly where I picked up, or where I left off. But I have L phi of x is equal to f of x. So what this says is that phi satisfies the differential equation, and also, if you look at the boundary conditions, notice what we get. Phi of 0 is equal to, well, it's going to be this, but where x is equal to 0. So we're going to have a 0 there. And then if you look at phi prime of 0, okay, because remember, for the boundary conditions, the Dirichlet, we only have information on phi of 0. The Neumann, it's only on phi prime of 0, but the Robin conditions are, combine these. A phi of 0 plus b phi prime of 0. Well, it's the derivative in the x variable, so it's 0 to 1 f of y. Wow, f of y, not g of t. F of y, dg dx of x comma y dy. And so therefore, if beta 1 phi of 0 plus beta 2 phi of 1 equals 0, then so if this is the boundary condition, so so if beta 1, let me say it like this: g of 0 comma y plus beta 2 dg wow, what is going on? I'm having issues here. dg dx at 0 is 0 comma y is equal to 0. Okay, so in other words, if g satisfies the homogeneous boundary condition, then phi will as well. So we're going to get beta 1 phi of 0 phi of 0 plus beta 2 phi prime of 0 is equal to, okay, so we're going to have the integral 0 0 to 1 f of y, and then we're going to get beta 1 g of 0 comma y plus beta 2 times, there should be a 0 here, times this, plus beta 2 times this dy equals the integral from 0 to 1 f of y times 0, because g satisfies the boundary conditions, equals 0. So then that should go away. Oh no, wait, what is happening? Okay, that needs to go away. Okay. So therefore, phi satisfies the boundary condition at 0. Okay, and similar things for the boundary condition at the other endpoint. So in other words, if G satisfies this problem right here, then phi defined by this expression here, phi defined like that, is going to satisfy this problem with the same homogeneous boundary conditions that G satisfies. And we've seen something like this before. I'll let you think about where we've seen something like this before when we were dealing with partial differential equations. So we've actually, this is one way to compute an explicit formula for a Green's function for an ordinary differential equation boundary value problem. But we've already seen a Green's function for a partial differential equation with a non-homogeneous partial differential equation. Okay, so I'll let you guys think about that and see and try to remember, or ask me about it in the discussion forums or whatever. Okay, so all of this part right here, this has nothing to do with the actual problem. I mean, it has something to do with the problem, but it's not solving the problem. So let me just kind of denote that. So first, this is why we care about the Green's function, and we'll use it for the next problem. Okay, so that's all this part right here. Okay, now I'll say, now let's find the Green's function. Now let's find the Green's function, and this is the solution to this problem. Okay, meaning, or this is the work. I should say this is the work for this problem. In other words, everything I did before is not like part of it's not part of finding Green's function. That's just again explaining why we care about Green's function. Okay, so we solve Okay, so our differential operator here is just phi double prime minus phi. So we're going to solve. I'm probably going to get lazy in just a little bit and just use primes to mean derivative, but not yet. So this minus g of x comma y is equal to the delta at x minus y. And then we want g of 0 comma y to equal to g of, 1 comma y, and both of those to be equal to 0. Okay, so we now solve. So the differential equation becomes g double prime of xy minus g of x comma y equals 0 on intervals that do not contain y. Note here, and below, the primes mean, my fingers are getting cramped, differentiation with respect to x. Okay, just don't want to write the frac over and over again. Okay, so this becomes a differential equation. The general solution then is g of xy. Okay, so here's what I'm going to do is g double prime equals g. So this is going to give me exponential functions. This is going to give me e to the power of a constant times e to the power of x plus a constant times e to the power of minus x. So this is going to be e to the power of x plus b e to the power of minus x, and this is going to be for x less than y, and then it's going to be basically this same exact thing, but with c's, d, and this is going to be for x greater than y. Okay, so writing it out like this, there's going to be a lot of tedious algebra here. This is one of those problems where when I sit down to write the solutions, I'm like, oh, this is going to be a pain. I mean, I just did it. All the problems that I assigned, I do, but that's just kind of scratch work. So I'm going to use hyperbolic functions here. So what are the hyperbolic trig functions? Let me just write out what we're going to get here. This is going to be a times hyperbolic cosine plus x plus b hyperbolic sine x. So what are these? So one way to think about these is if you think about the cosine and sine functions. If you think about cosine t sine t, this gives a parameterization for the unit circle. Cosh t sinh t, hyperbolic cosine t, hyperbolic sine t. As t goes from 0 to infinity, this gives a parameterization of a hyperbola. This gives a parameterization of a hyperbola. That's why they're called hyperbolic trig functions. And they're similar to sine functions. So for example, sinh of 0 is equal to 0, and we're going to use that. Okay, now, however we end up writing this, there's going to be kind of annoying algebra to do, but I'm hoping by using hyperbolic cosine and hyperbolic sines, it'll be more similar to the sine and cosine situation, which is, in my opinion, a little less tedious. Okay, so now the boundary conditions say that 0 is equal to g of 0y. So 0 is always less than y. So if we plug in x equals 0 here, what do we get? So look up what hyperbolic sine and hyperbolic cosine are. I'll just say hyperbolic sine is e to the x minus e to the minus x over 2, and hyperbolic cosine is e to the x plus e to the minus x over 2. So when you plug in x equals 0 here, you just get a, and when you plug in x equals 0 there, you get 0. So in other words, this says a is equal to 0. So by the way, if you're not comfortable with hyperbolic sine and hyperbolic cosines, there's two things to do. One is to get comfortable. Just go look at the Wikipedia article and just know what cosh and sinh are. The other option is just to, wherever you see cosh x, just write e to the x plus e to the minus x over 2. You don't have to use hyperbolic sines and cosines, but they're very helpful. And I think this problem is really going to show that they're a little more helpful to. It's a little more helpful to use sinh and cosh than it is to use the exponential functions. And if you look at my solution on problem num 1 for homework 9, I think you'll also see if you use hyperbolic cosine and hyperbolic sine there, that would also be easier algebraically. Okay, so this says a is equal to 0. Okay, then we know that 0 is equal to, in addition, g of 1 comma y, that's equal to 0. So we have 0 is equal to g of 1y. And what is this equal to? Well, this is going to be equal to c hyperbolic sine of 1 plus d hyperbolic sine of 1. Okay, so if we solve this, so then we can say if I subtract sinh from both sides, if I subtract the d sinh from both sides and divide both sides by cosh, this gives me c is equal to minus d tanh of x of 1. Okay. So then we're going to get, let me just make sure I did that right. So we subtract d, divide by that. Okay, so we're going to get the following then. Okay, so a is equal to 0, so that's just going to be like that. And then c is going to be equal to minus d tanh of 1. That's what c is, times that. Let me just go on ahead and factor out a minus, yeah, let me factor out a minus d. So we're going to have this. Okay, and I realize I have not compiled this in the entire video, so let's see where all of the errors I've made are. Okay. Oh, I didn't do a line. Okay, so not so bad. Okay, so now this is what we have. We've used the boundary conditions. Now we're going to use continuity. By continuity, okay, so why does the Green's function has to be continuous? If g had a jump discontinuity, then remember the derivative of a jump discontinuity is a Dirac delta function. So if g had a jump discontinuity, its derivative would be a Dirac delta function. And so its second derivative would not be a Dirac delta function. But its second derivative is a Dirac delta function. So if we think about what a Dirac delta does, remember these are distributions, so they're only defined in terms of integrals. Technically, not only, I mean, that's sort of the precise way to define them. So if you do like the integral of a function and a delta centered at x, or a delta centered at y, that gives you f of y. So if you do the integral of f and delta centered at y, that gives you f of y. If you do the derivative of f with the derivative of a delta centered at y, that gives you f prime of y. Okay, so in other words, if g has a jump discontinuity, its derivative is a delta, and then its second derivative is not going to be a delta. It's going to be something else. And so the equation that we used up here to show that phi of x defined in the way that we defined it satisfies the equation, that would no longer work. It would not give us L applied to g would be the derivative of a delta Dirac function, and so the solution that we got would not be phi of x, would be phi prime of x. So we'd get phi prime of x equals f of x, roughly. I'm off by a constant in what the derivative of the Dirac delta is, just based on, and that's going to be based on how you define things. At any rate, that's why we know it has to be continuous. So by continuity, we have to see that b sinh y. It has to be equal to this when we plug in x is equal to y. So this has to be equal, so b sinh y has to be equal to minus d times tanh of 1 cosh of y minus sinh y. So I think it's probably easiest to solve this for b. And so what we're going to get then is b is equal to minus d. Okay, what's going to go in the brackets here? We're going to have tanh 1 cosh y divided by sinh. So this is going to be tanh of 1 cosine divided by sine, or hyperbolic cosine divided by hyperbolic sine is cotanh y. And then sinh y over sinh y is going to be minus 1. So we're going to have like that. And I'm going to swap this around and do 1 minus that and get rid of that. So that's what b is equal to. Yes. So now we can continue to write out what g is. Okay. This should say g of xy. So then, okay, so d is whatever it is, and then b is equal to this. Okay, so let's see how this looks. All right. So now what we need to do is we need to use the differential equation to integrate to tell us what d is. By the differential equation, we have I there, don't I? We have 1 is equal to the integral from y minus epsilon to y plus epsilon delta of x minus y dx. But this then is going to be the integral of g double prime of xy minus g of xy dy. I'm going to do this in a couple lines here. Okay, and so this is going to be equal to g prime of y plus epsilon y minus g prime of y minus epsilon comma y. And then minus the integral. It's going to be the integral, but just with the g part now, because I did sort of like the fundamental theorem of calculus for the g double prime. Okay, now what's going to happen is that this, as epsilon goes to 0, g of x, this is a continuous function. We're integrating over an interval that's getting smaller and smaller, so that goes to 0. If you look at g prime, this is g prime. If you take a something doesn't seem right here. Nope. Okay, that looks right. The g is differentiable and the derivative is continuous. So what's going to happen is that as y goes to 0, this is just going to go to g prime of y comma y. And remember, we're doing the derivative in the x variable, and then minus g prime of y comma y, and this x there should be y. Okay. So this is going to be g of y plus 0, so it's the derivative coming from positive values of y. That's going to be the negative one. Okay, so that is 1 is equal to, okay, this is the derivative, and you know what, I'm going to make this sinh x. I'm going to get confused, so I'm going to do this. Sinh x minus that, and then get rid of the d here. Okay, so if we take the derivative here, we're going to have d on the outside. The derivative of hyperbolic sine is hyperbolic cosine. So this is going to be cosh y. We plug in x is equal to y. This is going to be cosh y minus tanh of 1 The derivative of hyperbolic sine is the derivative of hyperbolic cosine is minus hyperbolic sine. Wow. So we're going to get sinh y, and then minus d. Okay, what are we going to get here? It's going to be d times 1 minus tangent of 1 cotangent, or I don't know, I'm not sure how to say some of these words. And then the derivative of sinh is cosh, so this is going to be cosh y. And now we can simplify things a little bit. Let's see what's going to happen here. We're going to get d. Okay, so I'm factoring out a d. So the cosh y, I'm not going to do anything with that for now. Let's see if anything's going to cancel. So I've got actually maybe I will. So I've got a cosh y here. I have a cosh y times a 1 and a minus sign, so the cosh y's are going to go away. So I'm going to have a tangent 1 sine. Okay, so here's what I'm going to have. I'm going to have a tangent 1 sinh y, and then I've got a minus minus, so now it's going to be plus tangent 1 times hyperbolic cotangent times hyperbolic sine. So this is going to be plus, I'm going to write it this, plus cosh squared y, and then we're dividing by sinh y. Okay, let me just do this to see if I've gotten this. I need to look at it. Oh my goodness. Oh yeah, definitely need to go to a different line here. See, I told you the algebra would be easier. Okay. Now I have a tangent here. I forgot about that, so I'm going to go ahead and factor that out. Just because I need to see what's going on here to get the identities exactly right. Okay, so okay, sorry. Hopefully you saw the note that that I put here earlier, but I've made a mistake. It's a common mistake that I make. The derivative of hyperbolic cosine is not minus hyperbolic sine; it's just hyperbolic sine. So down here, let's see, where did the error come into play? So let's see. So there's I'm off by parentheses here, aren't I? Oh, this is just a mess. Okay, so this should be, oh no, wait. No, I'm not off by parentheses there. No, that's right, okay. So down here, what happened? So, I've made a mistake. Now I just need to figure out where the mistake happened here. I'm sure this is exhilarating, watching me get to work this out in real time, and not at all frustrating. Okay, so I did the derivative here. So I did the derivative here, and I got cosh y. That's correct, but that plus sign should be a minus sign. So that should be a minus sign. That's the error there. That's the only time I've done a derivative of cosh, and the derivative of cosh is just sinh. So this is what we have. So that minus that. Okay. So now let's work through what I'm going to have. So I have a cosh y here. Or d cosh y, that's still going to cancel with that d cosh y, so that's fine. But now I've got minuses, so this is going to be, this overall is going to be minus d tangent 1. So that cosh term there and that cosh term there go away. So I'm going to have minus d tangent 1, and then sinh y plus sinh y plus, why does that, did I make two errors that like offset each other last time? Oh no, so, Yeah. Wow. So I'm factoring out a minus d. So there's a plus there. So this is going to be sinh s minus cotangent, hyperbolic cosine. So this is going to be, if I write out explicitly what that is, this is cosh squared y over tanh y, like this. Okay. So now let me just make sure I've gotten everything correctly. So I need to have a minus d tanh y, tanh 1 sinh y, minus d tanh 1 sinh y, and then it's going to be minus a minus. So tanh 1 cotangent cosh y cosh s, that's what we have there, because the minuses are going to cancel. Okay, but now what we can do something similar to what we did before. Sorry, that's not correct. That should be cosh or sinh. I can factor out a sinh. So I can write this as minus d tanh of 1 divided by sinh of 1. And then here's what we're going to have in the brackets. We're going to have, not sinh of 1, sinh of y. I need to go home. Oh my gosh. Sinh squared y minus cosh squared y. So this is what we're going to get. Okay, so what is this? What is that equal to? What is sinh squared y minus cosine squared y equal to? Well, remember that I said that the hyperbolic trig functions were like the hyperbolic, were like the trig functions, but for hyperbolas. So the hyperbola that it parameterizes is the hyperbola x squared minus y squared equals 1. Just like the shape that the trig functions cosine t, sine t, the shape that parameterizes is the unit circle. That is x squared plus y squared equals 1. So therefore, cosine squared plus sine squared is equal to 1. Well, since cosh t sinh t parameterizes the hyperbola, whose Cartesian equation is x squared minus y squared is equal to 1, this means that sine squared minus cosine squared is equal to minus 1. Cosine squared minus sine squared is equal to 1. So now what we get is this is going to be equal to the following. This is going to be equal to d times this. D times that. Okay. And so now 1 is equal to that. We can now solve for d. Thus, what are we going to get here? We're going to get d is equal to sinh y over tanh 1. Sinh y over tanh 1. That is what d is equal to. Okay, now we're going to plug it into, where's our last g of xy? Okay, so we're going to plug it in and manipulate things. Okay, so g of xy, that's what d is equal to 2, so I'm just going to plug it here. Okay, it's really equals. I think I forgot equals somewhere. Did I have it up above? Equals there. Yeah, okay. So now I'm down here. Okay, so now what we're going to do is we're going to... All right, let me look to see what we have here. Okay, so now what we can do here... this sinh y, I'm going to move it all the way over here. So I'm going to do a lot of copying and pasting here. So this sinh y, I'm going to move it over here. So it's going to be sinh y, sinh x. So we're just going to have tanh 1. But when we distribute the 1 over tanh 1, that's going to go away. And what we're going to have is 1 over tanh 1, which is coach 1. So that this isn't, I need to fix the bottom one yet, so let me just make sure, let me just see what that looks like. Okay, coach 1 minus coach y, I think that's how you say it, I don't know. Sinh y, sinh x. Okay, so now what I'm going to do here, I've got sinh y, sinh x. I'm going to do this like a little more deliberately, so I'm going to do the 1. I'm going to move this sinh over there. And there's a reason that I want to do this. And now what I want to do is I want to actually factor out a cosh. So I'm going to factor out a cosh x here. So I'm going to take this out. So I'm going to have sinh y. Actually, hold on. What do I want to do? No, that's not what I want to factor out. I want to factor out the sinh x. So I'm going to factor out the sinh x. I'm going to have it here. That's a 1, but if I do that, I have to divide by this. So I'm going to have cosh x divided by sinh x. So that's going to be coach x. Okay, so let me see what I have here. Okay, good. So I still have this tanh. The 1 over tanh is going to get rid of that. 1 over tanh is going to be cotanh. Coach 1, and so this is now going to go away. Okay, good. So there's a couple of reasons I wanted to do that. One, I think this just looks as easy as it can go. This looks better than that. It looks a little cleaner. But also, there's this thing that we talked a little bit in class, where for the Green's function, g of xy equals g of yx. And this is not a property that we directly use to find the Green's function. So essentially, if we can get to the point, if at the end g of xy equals g of yx, then that tells me probably we didn't make too many errors, because we're not like using that directly to find g. It's just a property that g satisfies. And yes, you can see that there is a symmetry here, that g of xy does equal to g of yx. So for example, if x is less than y, this is g of xy. But then if you switch them, you're going to get this right here, just by this symmetry here. Okay, that is it for this problem. That was a lot. Thank you though for sticking with me. Or maybe we can think about the boundary conditions now. Let's look at g of when x is equal to 0. What do we get? Sinh of 0 is equal to 0. When we look at x is equal to 1, we have coach 1 minus coach 1, and that's also equal to 1. Okay, or that's also equal to 0. Okay, that's it for this incredibly long video with many exciting twists and turns. All right.